Hello, this is the first video on chapter 5. I'm going to try to finish the chapter maybe in 3 videos. So right now, this video, I'm going to talk about these 3 sections here, maybe 2 of them, see how much time we have. And then I'm going to do another video for these 2, and then another one for the third part of it. Okay, so let's get started. I hope you're doing well. So let me have more space on the screen, and then start with the first section, which is quadratic functions. So let me get that section from quadratic functions here. Let's see. Algebra. So let's open that. Now before I do any problems, I like to first get some white area here so we can work on the concepts first. So what we want to do, I think you have seen this before. So let's start it. What we want to do in this section is talk about functions that look like this: ax. So ax squared plus bx plus c, and we call these quadratic functions. You know about quadratic equations, things like x squared plus 5x plus 6 equals to 0. We solve this with quadratic formula, but of course if you get rid of this and then make that f of x equals to that would be an example of a quadratic function. We're going to talk about quadratic functions. So there are 2 ways to write them. One way is the general way, which is this right here, and another way is to write them this way, which is a and then x minus h squared plus k. Now, this form, an example of this form is like, let's say f of x equals to 3x minus 2 squared minus 4, something like that. Now, in this form is much easier to work with them than in this form. So what we want to do, we want to talk about both and do a bunch of examples of each. Now in this form, we can think of this as basically x squared, which is the graph you're familiar with, right? And the graph of this would be the graph of this with application of what? These transformations. There are 3 transformations here. Remember transformations: vertical stretch, shift to the right, and shift down 4. Now if you apply this transformation to this point, which is at 0, 0, where does it go? Well, we have to multiply the y value. Remember how we did that with transformations? We have to multiply the y value by 3 and then subtract 4. If I multiply 0 by 3, subtract 4, I get negative 4. And then x, I have to subtract 2 from it. So 0 minus 2 is minus 2. We have to add 2 to it, not subtract, because that's what? That's move to the right 2 units. So add 2 units to it, we get 2. So it looks like we have the x coordinate of this point which is the vertex of this, is called the vertex of the parabola, goes to this point, 2, -4. And 2, -4, we could get it from here. See, 2 and -4. So in this form, we say that the vertex is always at point H and K. Whatever H and K are, that's where the vertex is going to go. And notice that there is a minus in the formula, so this has to be a minus here. So if you get like x plus 2 here squared, you have to write it as x minus -2 squared. Then h is -2. Okay, so let me continue here. Oops. There. Okay, and also we know that the number right here, if it's negative, that means we have a reflection over the x-axis. And if it's positive, of course it stays the same way, right? So that means if A is positive, then we have this thing opens up. And if A is negative, this opens down. Okay? All right. Now, what else do we need to graph these? Well, we also need what? We also need the x and the y intercepts. The y-intercept is easy to find. The y-intercept is just f of 0. So we substitute 0 here. And we substitute 0 for x, right? And we can find the y-intercept. That's easy. So we just say y-intercept would be 0 and f at 0, right? And the x-intercept is going to be what? It's going to be when f of x is 0. That means we have to set, so x-intercept is going to be a x minus h squared plus k equals to 0. That's how we find x-intercepts and y-intercepts. And we are done. And we can easily graph one of these. So let's look at it. Let's look at an example. Let's say f of x equals to, let's see, 2x minus 1 squared plus 2, right? So since a is positive, we know that this opens up, right? Because a is positive. And also we know the vertex is at 1 and 2, right? So let's graph this. Let's graph it over here. So 1 and 2. That's the vertex. And does it open up or down? Opens up, so it doesn't really have x-intercept, because we know it's going to go that way. It's not going to cross the x-axis here, right? This is x-axis. Okay, so what is the y-intercept? Well, the y-intercept is going to be f of 0. And f of 0 is 2 times 0 minus 1 squared plus 2, which is negative 1. 0 minus 1 is negative 1 squared is 1. 1 times 2 is 2. 2 plus 2, 4. So y-intercept is at 4. That's 3 and 4 right there. Okay, now we can graph this. We know it's going to look like, looks kind of like this over here, and it goes up. And there is a line in the middle here that cuts the graph in half, and that line goes through this number 1. So here we say that x equals to the x coordinate of the vertex, right? Remember, that was the x coordinate of the vertex. And it turns out that this is always the case, that x equals to h is a line that cuts the graph in two parts, so we call it line of symmetry, that line. So we call it the axis of symmetry. Okay, so axis of symmetry x equals to 1, and then we know the other part is going to be like symmetric with that, and well, maybe a little bit like that. So that's how we graph this one right here. Now the question is, if we have one of these that opens up, this point right here is the minimum of the function. It's called the global minimum, or you can call it relative minimum. Is right here is a relative minimum. Compared to other values, this is the smallest. But this is smallest compared to all the other y values, you see? So it's a global min. And if we have one of these that are open down, then that one is the global max. So now notice that when we say min and max, here for example, the minimum here is nothing but what? The y coordinate of the vertex. So if we have one of these, the y coordinate of the vertex is going to be the min, and if we have one of these, the y coordinate of the vertex is going to be the max. And the x coordinate is where the min or max occur. That means at what value of x the y value is min or max. And that's, of course, that is the x coordinate of the vertex, right? So these are, in both cases, these are h's, but the y coordinates is either min or max depending on whether we are opening up or down. Okay, so that's how we deal with this form of quadratic function. What if we have this form? Well, this form is exactly the same procedure to graph it, except the vertex is not clear over here, right? The vertex here is h and k, but what about here? So it turns out, and it is in the text, and you can read it in this section, is application of trying to make this look like this, goes through a procedure that is, we have covered already, is called completing the square. And if you complete the square for this, you end up with this form. But what about the h and k in terms of a, b, c? Well, it turns out that our h here is negative b over 2a. Now, k has a more complicated formula in terms of ABC. We don't have to use that because we know k is what? K is the y coordinate when x is h. So if x is this, then k is nothing but f of that. That's how we deal with the vertex. So the vertex is given this way. Everything else is the same way we find the rest of it. So let's let's convert this form to this form, so we can see it's the same thing. So if we want to convert this to this form, we're going to have to do what? We have to do f of x equals to 2 times, now we have to expand this. Remember, a minus b squared is what? Is a squared minus 2ab plus b squared. So let's do it that way. So it would be x squared minus 2 times 1 times x is 2x plus 1 and then plus 2. So that is what? That is 2x squared minus 4x plus 2, which is 2x squared minus 4x plus 4. So that's our f of x. Now, does this formula work actually to find h and k in this form? So suppose we are given this. Now we know what h and k are, but let's see. Let's just reuse this formula. So here a is 2, b is negative 4, and c is 4. So let's see. h has to be negative b, which is negative 4, right? And over what? Over 2 times a, which is 2. So that's 4 over 4, which is 1, and that's the same number that we found here, right? Right here. And f of 1 is going to be basically, you put 1 in here, we get 2 1 squared minus 4 times 1 plus 4. Well, that's 2. That's 6. 6 minus 4 is 2. So that's 2. So it's the same that we have here, the vertex. And the rest of it is the same. If you find the x and a y intercepts, is the same way, right? So if you were to find the y-intercept of this, you just substitute 0 for x, you get 4. And the x-intercept, you set this equal to 0, and you're going to see it doesn't have any real solutions. So we don't really need to have to find the x-intercepts here because there is no x-intercept. Okay, now that we understand what is going on here, we're going to go to this section and make it a little bit bigger so we can see what's going on. Maybe that big. I'm going to start with number 6. And it says, for the following exercises, rewrite the quadratic in what? In a standard form. So let's do that. So we are going to write this in a standard form. In what form? In this form. F of x equals to a x minus h squared plus k. Now, so we know in this form, here a is 1 and b is negative 12, right? So let's use that. So a is 1, so a is the same. A is a in both forms, right? Now, what is h? Well, we know h is negative b over 2a, which is negative b over 2a. What is b? Negative 12. What is a? 1. So that's 12 over 2, which is 6. So that is what? That is 6 here. That is 6 here. There. All right. Now what is k? Well, k would be f of 6. So that means we have to just substitute 6 for and plus 32. If the numbers are big, just use calculator. But that number is, I have negative 4. It's going to be negative 4, and it's right here. So, so that would be negative 4. Now, it's this plus negative 4 is the same as minus 4, right? So that's the standard form of number 6. Let's do number 8, that one. So that one, again, what are we going to do? We want to write it in this form. Ax minus h squared plus k. Now, here a is 1, and b is negative 1, and c equals to 0. There is no c here. So we know that h is negative b over 2a, which is negative b over 2a. Now b is negative 1, and a is 1. So that's 1 over 2, right? So that's our h. Now we know our a is 1, and our h is 1/2. So we just need k. Again, we substitute 1/2 in this function. What do we get? F of 1/2 is 1/2 squared minus 1. 1/2 squared is 1/4 minus 1/2. And so 1/4 minus, multiplied by 2 to get the same denominator. So that's 2 over 4. And that's, you write the denominator and subtract the numerator. 1 numerators. 1 minus 2 is negative 1. So that's a negative 1/4. Okay? So that's how you convert it. I mean, that's how you write it. All right, now we want to do, let's do another one. Let's do see, one of these. Rewrite in a standard form. So let's do number 12. Number 12, okay? So we want to rewrite it in a standard form again. It's again the same kind of stuff, right? So let's write it here. So f of x equals to ax minus h squared plus k. So it would be, what's a? A is 2. So that's 2. X minus h, and then plus k. So we don't know what h is. Well, that h is negative b over 2a. What is b? Negative 6. What is a? It's 2. So that is 6 over 4, right? Which is 3 over 2, right? 3 over 2, so this is 3 over 2. And it's positive, so we just put, if it's negative, we have to put minus negative, right? Now, what is k? Well, k would be f of this number. So it's calculated right there. It's negative 9 over 2. Okay, that's that. Let's do, okay, it says for the following, determine whether there is a min or max and then find it. Okay, and the axis of symmetry actually, and axis of symmetry too. All right, so we talked about this. In order to figure out whether we have a min or max, we have to figure out whether we have one of these or we have one of these. In this case, since a is positive, we have one of these. So we don't have that, we have this. So we know the min happens at what? At the vertex right there. So this has a min, and it happens here. It happens at h, and its value is given by the y-coordinate of the vertex. So all we have to find is the vertex, because if we find the vertex, we also have the equation of the axis of symmetry, which is x equals to h, right? So we know h is, again, negative b over 2a, and that is negative, well, let's put it right there. So what is b? b is 10. Now what is a? 2. So that's negative 10 over 4, which is negative 5 over 2. So The mean happens at this x value. And what is the mean for this? Well, the mean would be f of negative 5 over 2, which is right here. So if you substitute negative 5 over 2 for x, and then do the arithmetic, you get what? You get negative 1/2. Now, we could do it with a calculator this way. So we can use a calculator, go to y equals 2, and then let me turn off my plot. I can use y equals 2. So we put this function in y1. Okay, so we did 2x squared plus 10x plus 12. So this is y1, that's our function. So we go to home screen, and we're going to find y1 in the variables here. So we go to variables, you go to y variables, and then go to function. Then the first one is y1, and then we put parentheses. So we want to find f y of, or f of, doesn't matter, here is called y of what? Of negative 5 over 2. So we put negative 5 divided by 2. And that's negative, and you can convert it to fraction here. Press math, enter, enter. Negative 1/2. So that would be negative 1/2. So this is the mean, and this is at what x value this function has that mean, right? All right, so let's do a few more of these. What about number 16? Well, the same thing. Oh, we didn't talk about the axis of symmetry. Axis of symmetry on the previous one was just x equals to negative 5 over 2. Now for this one, again, what do? We see first that a is negative. So a is negative 1, so this is one of these, right? And we know what happens at the vertex is that this function has what? Has a max. So we got some x value which we know is h. This would be the max, right? So let's find h first. We know a is negative 1 and b is 4. So h is negative b over 2a, and b is 4, and a is negative 1. So that's negative 4 over negative 4, which is 1. So h is 1, and this number is f at 1. So what is f at 1? Is negative 1 squared, is like that, negative 1 squared plus 4 times 1 plus 3. And that is what? That is 1 squared is 1, and then negative is negative 1, right? Because this negative is not to the second power, only x is to the second power. So plus 4 plus 3, so that's 7 minus 1 is 6, so that is 6 right here. So that's 1, and, well, what did I do? Oh, my fault. What did I do? I put 4 here. Ah, that's not 4. That's 2. Okay, so that's a 2. My fault. So let's put a 2 here. That's why I check to make sure I don't make arithmetic mistake. 2 and 2 here. So that would be a 8. And 8 plus 3 is 11. And this is a 4, because 2 squared is 4. So that's the 7. Okay? So that's 7. So the max is 7, and it happens at 2. All right. Again, let's do another problem. Let's do 21. It says determine the domain and range of a quadratic function. Okay? Again, before we do that, let's realize that if we have something, let's say we have something like this, right, and the vertex happens to be here, we know that the y-coordinate of the vertex is k, right? Now, for all quadratic functions, the domain is all real numbers. It doesn't matter what function you have, domain is always that, the natural domain over there. You can restrict it if you want, but the natural domain for quadratic function is all real numbers. Now, what about the range? Well, the range depends on whether we have one of these or maybe we have something like this, right? That opens down, and the vertex can be anywhere. Could be here, here, doesn't matter. So that would be k, and k in this case would be a negative number. And then this would be h. Again, domain is the same for both, but the range of this one starts from k and goes to infinity. So it's k, and k is included. And for this one, the range is starts from negative infinity and goes to k. So we have negative infinity to k, including k, right? So what does that tell us? It tells us that if you know the vertex, you know the domain and range, right? And you have to know, of course, whether it's opening up or down. Then you know the range and domain. So here we know A is 1, right? So that means this thing opens up. So all we have to know, I know the domain. The domain is all real numbers. Now, what is the range? Well, the range would be from this number on to infinity. So the range is going to be from some number to infinity. Now, we don't know that number. That number is k, and we know k is f of h, right? But in this case, k is what? K is right here, right? Because we know the vertex. The vertex is a 3 and 2. So basically what we have is the range is going to be from 2 to infinity, including what? Including 2. All right, so that is, let's do another one quickly. It says, for the following, find a general form if you're given that much information, okay? Well, let's do that. So we are given this much information. So we have h and k. So let's write it in standard form first. So it's a times x minus h squared plus k. So what is a? What is h and k? Well, h is 2 and k is 0. And we don't know what a is. So basically what we have is a and then x minus 2 squared. But we know a point on the graph. That we know that. What does that mean? It means that there is a point on the graph where we have the x coordinate is 4 and the y coordinate of the point, right? So that's the x coordinate, and the y coordinate of the point is 4. So that means whenever f of x is 4, x is 4. So we put 4 equals to a times 4 minus 2 squared. 4 minus 2 squared is 2 squared is 4. So 4a equals to 4. So a equals to 1. So the formula for this function is 1x minus 2 squared. And if we want to write it in general form, all we have to do is what? Just do the operations here. X minus 2 squared is x squared minus 4x plus 4. So general form and standard form. All right, that was 26. Now 30, let's do one in this category here, 34. It says sketch a graph of the quadratic function and give the vertex, axis of symmetry, and intercepts. Okay, so let's do this right here. Okay, so we know that x squared minus 2x, okay? So we know we can convert it to this form. Again, ax minus h squared plus k. What is b here? We know h is negative b over 2a. A is 1, and b is negative 2. So that's 2 over 2, which is 1. So h here is 1, and a is 1, right? So basically 1 and x minus 1 squared. Now what is k? K is f of h, right? Which is 1 squared minus 2 times 1, which is 1 minus 2 is negative 1. So that's a negative 1. So axis of symmetry here would be x equals to 1. That's the axis of symmetry. Now, what are the intercepts? Well, the y-intercept is going to be f of 0, which is 0 minus 1 squared minus 1. Negative 1 squared is 1. 1 times 1 is 1 minus 1 is 0. So y-intercept is 0, 0. Now, what about the x-intercept? Well, the x-intercept is when x minus 1 squared minus 1 equals to 0. So x minus 1 squared equals to 1. We take square root of both sides. We get x minus 1 equals to plus and minus 1. So x equals to plus and minus 1 plus 1. Move that negative 1 to the other side, change the sign. So you have to take the plus first, or take the plus and then take the minus. So that would be 2, or if you take the minus is 0, right? So this, we have the x-intercepts is 2 and 0. We can easily graph this. So where is the vertex? The vertex was at, let's see, oops, where did it go? Come back here. Where did it go? There we go. So the vertex was at, oops, trying to get this, there we go. So the vertex of this is at 1, 1, right? See 1 and 1, negative 1, right? That's the vertex. So h was 1, so that's the vertex right there. So 1, negative 1 is 1, negative 1 is right here. And so where is the y? It opens up because a is positive. So y-intercept was 0, 0. So y-intercept is 0, 0. That's another point. And the x-intercepts are 0 and 2. So 0 and 2. So it opens up. We know it's going to look like this and that. And the axis of symmetry goes through right there, x equals to 1. Right? That's axis of symmetry. So these are the x-intercepts right here. That's the y-intercept right there. Axis of symmetry and the vertex, which was 1 and -1. Okay, so that's number 34. And let's do one more. And that is number, still 146. Sorry about that. I know in the video it doesn't look good. So it goes up quickly, but here we go. So we want to use these numbers to find the equation because we have a bunch of points. So what we can do is, since we have so many points to choose from, we can use them to graph this, to write the equation for this, right? If we assume it's quadratic. Now, there are situations where in application problems, we find a bunch of points that look like that. Is this quadratic? Well, we don't know. We can actually find a quadratic that goes through all these points, right? Or maybe you find a situation where the points look like that, and you want to find a quadratic function that goes through them. Computers and calculators can do that easily. So what I'm going to do is I'm going to show you how to do it with the calculator. Now to do that, you have to graph these points. These are points, right? These right here are ordered pairs. So we got how many ordered pairs? We have 5 ordered pairs, and these are x values and these are y values. So to graph it with a calculator, we go to turn it on, we go to y, make sure there is nothing here. And then we go to stat, edit. You see there are 2 columns here. There is L1 and L2. I already put these numbers in there so I can save time. So you see I put the x values. As you see, x values are right there, right? And so we have -2, -1, 0, 1, 2. So you go over here and you put -2 and you press enter, -1 and press enter, and so forth. Then you go to L2 and make sure you're on the first one and put the y value 5 and then 2, 1, 2, and so forth, right? After you have your L1 and L2 filled with x and y, then you go to second, stat plot here, turn the first one on, then with the default is off. So you go to on, press enter, and then go to the second row, pick the first type. There are 6 different types of graphs. You want the first one, which is a scatter plot. You want that one, so press enter. Then go down to L1. You have to put L1 there. If it's not there, just put L1. See, L1. Second, number 1, L1. And L2 for Y. And then pick one of these marks. Let's pick the bigger one, the biggest one. And then we go to zoom 9. You see? So these are these 5 points. They look quadratic. So the calculator can find a quadratic function for you. So what you do is you go to stat, calculate, and then you go find quadratic regression, this one. Put it on home screen. Let me clean the home screen and do it again. Stat, calculate, quadratic is number 5. And then you have to tell the calculator where the x's are, x values, and where the y values are. So x values are in L1, and then comma, y values are in L2, and press enter. You see? Calculator found a quadratic for us. What's the quadratic? The quadratic is ax squared plus bx plus c, where a is 1, b is 0, so 1x squared plus 0x plus 1, and c is 1. So the function that goes through these is x squared plus 1. Now you can go to y equals 2 and put that function in there. You can type it in, or you could just go to memory of the calculator under variables and go to statistics and go to equation right there. And it's the first one. There. It puts it there. Of course, we could have just typed it in. But when you graph, now you see a model that goes through the points, right? So calculator found a quadratic that goes through those 5 points. Okay, so that is this section, 5.1. So I want to talk about 5.2. What is 5.2 about? Well, 5.2 about power functions and polynomials. So let's talk about them quickly. And then we do some examples from that section. So what is a power function? Well, a power function is a function that looks like this right here. So it looks like, let's say k, some coefficient, times x to some power, where k and p are real numbers. Now, what does that mean? Well, let's look at some examples. Let's say p is an integer. If p is an integer, then we get, and k is, let's say, 3, then we get something like this, right? If p is, let's say k is always a real number, let's say square root of 2, and then the power is a negative number, that would be that, negative integer. Or maybe k is like, let's say 5, and p is a fraction, let's say 2/3. Or maybe k is an irrational number, and the p is also an irrational number, something like that. So all of these are examples of a power function. That's what we call these, power function, right? So power functions are one term, first of all. They have only one term, and that term includes a coefficient, a variable, and then exponent. The exponent and the coefficient are real numbers. And all of these are power functions. Now, what is a polynomial? Now, a polynomial, let's call it p of x, is a combination of power functions that have only p has to be a positive integer, has to be a positive integer. So these cannot be used for a polynomial, only these. So if the power is positive integer, then we have a polynomial. So a polynomial could be just 0, that's a polynomial, or it could be a combination of these. So the combination means bunch of them. Let me give you as an example before I give you a general formula. So for example, 3x to the third minus 2x to the second minus 3. That's a polynomial because all of these are what? Are these a special kind of power function with the exponent of positive integer. So in general, they look like this. Some x to some power n, whatever n is. And then we usually like to keep the biggest exponent first. So we change the order so we have the biggest exponent first. And we call that the leading term. That's the leading term of the polynomial. And then the coefficient of it, we call it a sub n. So a sub n means the coefficient of x to nth power. And then the next one would be a sub n minus 1, x to n minus 1. And if you continue this way, well, if n is an integer, positive integer, if you keep subtracting 1 from it, you end up with 0 eventually. And we stop. Because if we keep subtracting after 0, we get negative numbers, and we don't want that. Remember, p has to be positive integer here. Okay, so the last one is going to be really x to the 0th power, and then a sub 0 for the coefficient. All right, so we usually don't write this x to the 0th power because it's just 1, doesn't change anything. So the last one is just a number. We call it the constant term. And this one here is the leading term. This number right there is the degree of the polynomial. So for example, this polynomial is a third degree, and the leading term is 3x to the third. Okay? So those are polynomials and power functions. So let's do some examples first before we do some more concepts. So we're going to go to the second section and do some problems from that section. Again, we want to make them a little bit bigger. You can see it. So let's start with these problems here. We want to know whether these are polynomials, power functions, or neither. Is this a power function? Yes, because it looks like the power function that we talked about. So let me grab this part and so we can write on it. So is this a power function? Yes, because it looks like what? It looks like f of x equals to kx to p. K here is 1 and p is 5. So this is power function. What about, let's put p for power function. This one, well, this is the same as x to the 6 because you have to multiply the exponents. So again, k is 1, p is 6, power function. What about this one? Well, each of these is like a power function with the integer power and they're combined. So this one is a polynomial, PL, polynomial. And this one is neither because it doesn't look like a polynomial and doesn't look like, you cannot write this as a sub n x to n plus, what we talked about. Also because the domain of this is not our real numbers because the denominator cannot be 1 or -1. So it's not a polynomial. And it's not a power function. All right. Now, what about some more? What about number 10 and let's say 11? It's 10 and 11. Pen is not working. There you go. So number 10. Now, if we want to write this function 2x times x plus 2 times x minus 1 squared in a form like a polynomial, like this, dot, 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 and then the last term. Well, we don't have to really multiply all that because all we need to know is this one and that one. And to find them, we can think of every one of these factors as a polynomial and write the leading term of each of these. So what's the leading term of this polynomial? Well, is itself, because it has only one term. You can also call this a power function, right? Because it's by itself. But when you multiply, this is a polynomial. It's not, f of x is not just that, right? So this is not a power function, it's a polynomial. So the leading term of this polynomial is x, and the leading term of this polynomial is x squared. So what we have is 2 times 1 is 2, and this is power 1 and this is power 1. So x times x squared is x to 1 plus 1, 2 plus 2 is 4. You have to add the exponents. So that's the leading term, and it's going to be plus a bunch of stuff. And the last one is going to be the constant term, and we can find it without really multiplying all that. So if you think of this as a polynomial, then there is no constant term, right? Because it has only one term, that means the constant term is 0. So the constant term of this one is 0. Constant term of this obviously is 2. And the constant term of this is when you raise -1 to second power, which is 1. Now what's 0 times 2 times 1 is 0. So the constant term is 0. So this is a polynomial that is going to look like something like this. We don't have to write it out completely. You just have to figure, is it a polynomial? Yes, and this is the leading term. This is the constant term. And the degree of it is actually 4. So that's number 10. Now what about number 11? Is that a polynomial? No. Is that a power function? No. Why? Because it's not a variable and a coefficient and a power. In fact, if you look at it, that has variable in the exponent position. That's not a power function and it's not a polynomial. In fact, it's a function we call exponential, and we're going to talk about that in the next chapter. All right, so let's talk about a few more of these. I'm going to talk about number, let's say, 15. So what we want to do here, it says for these, find the degree leading coefficient for these. So leading coefficient is basically the coefficient of the leading term, right? So let's see. So for this right here, the leading term of the first one is just x, right? The leading term of this is -x squared. And the leading term of this is just 2x. So positive 1 times a -1 is -1 times 2 is -2. And this is x to the first power, and this is x to the first power. X to the first times x to the second times x. So that's x to 1 plus 2 is 3 plus 1 is 4. So that is the leading term of this polynomial if you expand it. And the leading coefficient is going to be -2. Now what about the constant term? Well, constant term of the first one here is 0. Constant term of the second one is 4, right? Even though it's written this way, you can write it this way, right? It's the same as that. Leading term is -x squared and constant term is 4. And the constant term of that one is 1. So this is 0. 0 times 4 times 1 is 0. Okay, now it's a polynomial that has a leading term, that, and the leading coefficient of -2, constant term of 0, and the degree of what? 4. All right, and what else we're going to do? Let's do a few more. Let's do number 17. So in number 17, again, what do we want to do? We want to talk about the end behavior. What is end behavior? talk about that. So it turns out that a function like the power function, right? When p is an integer, negative or positive integer, then we can think of this as we can talk about the end behavior of it. The end behavior of it, if p is an integer, is going to look like either this. What do I mean by that? I mean, when x approaches infinity, that means when x values are really large on the right, what happens to the y value here? What happens with f of x? And when x goes to the left to negative infinity, what happens to the y value? If we look at different power functions with the power, special ones with the power integer, right, negative or positive, then we're going to have four different types of behavior. Either it goes up and up on the right and left, or it goes down and down, or on the right it goes up, on the left it goes down, or the other way around. On the left it goes up, and on the right it goes down. How can we determine that? Well, that's easy. Let's look at this example, x to the fourth power. So we're going to know what is going on at the ends. We don't care what's going on in the middle, just at the ends. At x equal to x approaching infinity and negative infinity. When x values are over here, what do the y values do? Do they go up? Do they go down? Do they stay the same, right? So the way we figure out is by letting x be infinity, basically. So what's f of x? Well, f of x is x to the fourth power. That means x approaches infinity is like infinity to the fourth power, which is infinity. So that means when x is infinity, goes to infinity, f of x also goes to infinity. So if I have a point over here has a big x value, then the y value is also big. So if you follow these points, they're all going to kind of look like that. They go this way, right? When x is big, y is big, so we go that way. When x is big, if y is negative infinity, we'll go this way, right? So what about when x goes to negative infinity? Well, we substitute negative infinity for x, and since the power is even, then negative to the fourth power is positive, and infinity to fourth is just infinity. So still the same way. So this function behaves like this at the ends. All right, and that's number 17. Let's do, let me see if I have another one here. Yes, we could do number 19 too, now that we are at it. Let's do number 19 as well. So number 19. So what we have is, again, we want to know when x is infinity, goes to infinity, what happens with that? Well, that becomes negative infinity to the fourth power. Now, infinity to the fourth is infinity, so we just have negative times infinity, which is negative infinity. So that means on the right, when x is really large, y is really negative. So it's going to look like this. Now, what about on the left when x is negative infinity? Again, we put negative infinity for x in the f of x. Now, don't multiply these because you have to do the power first, exponentiation. Negative to the fourth is positive, so that would be a negative, and then this would be positive infinity, which is what? Again, negative infinity. So on the left also, it behaves like that. All right, So that was number 19. So what about number 21? Now, how do we deal with polynomials? Because polynomials they have more terms, it's not just one term. Well, it turns out that when we have a polynomial and you order it with the leading term first, then the leading term actually determines what the end behavior of the function is going to be. When x is really, really large, the values out of the rest of the terms are so small compared to that they're like pocket change. So the main value of the function comes from the first term. Think about it. If you have x to the fourth and x to the third and x to the second, when x is, let's say, 1,000, now 1,000 to the fourth power, that's 1 with 12 zeros. 1 with 12 zeros. That's a lot of zeros right there, right? But x to the third power is going to be 1 with 9 zeros. Now, 12 zeros and 9 zeros, that's a major difference between the two. So as x becomes bigger and bigger, the difference between them becomes larger and larger. So the rest of the terms, they're just pocket change compared to the first one. Okay? So that's the idea. So if we want to find the end behavior of a polynomial, we are going to have to work with only the leading term. So the end behavior of this polynomial basically is determined by this. And we know how to deal with that. Just what? Just for on the right-hand side, when x goes to infinity, we're going to take this and put positive infinity in there. Positive infinity to the fourth is positive infinity, times 2 is still positive infinity. That negative makes it negative. So on the right, we have this behavior. Now what about on the left, which is negative infinity? Well, it's going to be negative 2 and negative infinity to the fourth. Negative infinity to the fourth. Negative to the fourth is positive, and infinity to the fourth is infinity. Negative 2 times infinity is negative infinity. So on this side is also negative. So this polynomial behaves like this at the ends. Okay? And 22, well, again, this is the leading term. We're going to look at that only, right? When x goes to positive infinity, we get 3 times positive infinity to the second, which is positive infinity. So it behaves like this. And on the left, when x approaches negative infinity, we have 3 times negative infinity squared. Negative to the second is positive, so that's just positive infinity. Because when you multiply this by 3, you still get infinity. So it's this way. Now, you should have known this because this is what? This is quadratic and opens up. So end behavior on the left and right looks like this. Okay, and let's see. Let's do one more. Number 25. So in 25 it says, let's see. It says for the following, find the intercepts of the function. Now, before I do that, let me explain a few things. We said that a polynomial looks like this. A sub n x to n plus dot 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 plus a sub 0, right? Now, it is proven in mathematics that any polynomial can be factored into something like this. If it's nth degree, it will have n of these factors. I'm not going to write all of them, of course. I don't know how many. And the factors look like x minus something, x minus something, and x minus something. And these somethings are actually numbers that there are n of them because it's nth degree. So C1 through Cn are complex numbers. We're going to talk much more about this in future sections of this chapter, but for now, any polynomial can be factored. That's a mathematical theorem that has been proven. It's not that easy to prove, but it's been proven and accepted. And it's not that easy to factor polynomials either, but we can do it, and we know that we should be able to do it. But how do we do it? That's what this chapter is all about. All right, by the time we get out of this chapter, you should be able to factor some polynomials, not all polynomials, but some. So let's look at some examples to make it kind of clear what this theorem is saying. So if you have something like this, right, we know how to factor this. So the factors would be 1 times something, and those two numbers, you know, are 2 and 3, right? So this theorem says we can always do this. That means it's always possible to find these numbers, I put them here, and then multiply these factors to get the original polynomial. Now, these numbers turns out to be, look, what happens if you let this be 0? Well, if these are real numbers, then if we want to solve this equation, we're going to have to do that. We have to set this equal to 0, get what? -2, or set the other one equal to 0 and get -3. So if we have factors like this, and these are real numbers, the opposite of these numbers, you see, this is +3, but that's -3. This is +2, this is -2. The opposite of these numbers are x-intercepts of this function when you graph it, right? So polynomials have, you know, they might have a bunch of x-intercepts, right? They might look like that. These numbers right here are actually opposites of these numbers that are given over here if they are real numbers. Now, there could be also complex imaginary numbers. We're going to talk about that in the future sections. But for now, these are real numbers. These are real numbers right here. So the intercepts, the x-intercepts of a polynomial, if you're given in this form, they're just opposites of these numbers. And the y-intercept is easy to find, just substitute 0 for x. So here, in this problem, if we were to graph this, which we're going to do in the next section, but for now, if we were to graph this, we would know the x-intercepts and the y-intercepts of y-intercept of this. There's only one y-intercept, but there could be many x-intercepts. So the x-intercept of this one would be, if you set that equal to 0, we get what? We get 1. So 1, and then this one, if you set equal to 0, we get -2. So -2. And this one, if you set equal to 0, we get 3 and 3. Those are the x-intercepts of this function. And the y-intercept of this function is just f of 0, which is 2 times 0 minus 1 times 0 plus 2 times 0 minus 3. Common mistake is to say that f of 0 is 0. It's not, because these parentheses are not zeros. So this one is actually -1, this one is 2, and this one is -3. So the y-intercept is 2 times -2 times 2 times -3. So it's going to be positive. 2 times 4, 2 times 2, 4, 4 times 3, 12. So it's like 12. We assume this is 12 here. So that's what it looks like. And if you know the end behavior of this, you can actually graph this, and we're going to do that in the next section. All right, and let's do a few more. What about number 31? Now, if we were to graph polynomials, when you graph polynomials, people notice that they, of course, have n behaviors, but what happens is that polynomials are continuous and smooth, first of all. They're continuous and smooth. They have no breaks. They don't have sharp corners either. There are no sharp corners in polynomials graphs. And also, they don't have behaviors like approaching certain horizontal asymptote like this. And they don't have any limitations in the domain. So if you find like a function that is approaching a vertical line but never crosses it, that's not a polynomial. It's not a graph of a polynomial. So also people realize that depending on degrees of the polynomial, these are called turning points. Turning points means the function changes behavior. This is kind of a little bit off, but it looks like it's coming down here and goes up. So there's a turning point somewhere right there. Comes down and then goes up. That changes behavior. So 1, 2, 3, 4, 5, 6. So there's a theorem that says a polynomial that is 6th degree, nth degree, right, can have n minus 1 turning points, right? So what does that mean? That means that if we have, how many do we have? 1, 2, 3, 4, 5, 6. So, well, it's the turning point is actually over here. It's not there. It's going down and goes up. Here we go. So 1, 2, 3, 4, 5, 6. So 6 can be the maximum number of turning points it can have is n minus 1. That means n minus 1 is the maximum number of turning points it can have. But in this case, we have 6 of them. So what should the degree be for this to make sense, this rule? Well, it looks like the degree here has to be 7, because anything less than 7, let's say n is 5, 5 minus 1 is 4, and 6 cannot be smaller than 4, right? So with this theorem, we can figure out that this has to be at least 7th degree. Why? Because it has 6 turning points. So that's the idea of number of turning points. All right, now here in this problem, how many turning points do we see? We see 2, right? So that means n minus 1, right, has to be at most what? I mean, let me put it this way. So 2 is number of turning points. So that means the degree has to be what? The degree has to be at least 3. 3 minus 1 is 2. If it's 2, 2 minus 1 is 1, and then 2 is not less than or equal to 1, right? So the smallest possible of smallest possible of degree, the smallest possible degree of this polynomial has to be 3, right? Because it has what? At most n minus 1 turning point. So it can't be can be bigger than that, right? So since we have only 2 turning points here, n has to be at least 3. Now, just because it's a 3rd degree That doesn't mean it has to have two turning points. It means if it's third degree, then it has to have either no turning points, right? One turning point or two. That's what it means. Okay. Now, so let's look at now. Also, there is another piece of information here, and that is what? That is the three what? Three roots or zeros or the x-intercepts. That's what they're called. So that means this polynomial looks like at least is going to be x, x, and it's x minus what? Minus -4. This would be x minus -1. This would be x minus 4. Now, we don't know what a is here. We don't know whether there are more. Maybe there are more, but they're complex numbers. Let's say it's 2i or something. They're not real numbers. So we can't really know more about this. We're not given more information. We know that it has three roots, so it's going to be at least third degree, and also has two turning points. That's another reason it has to be at least third degree. All right, so that's number 31. Now, what about number 33? Let's do a few on 33. Well, we passed it. Well, number 33, how many turning points? Again, is 1, 2, 3, 4, and it has 1, 2, 3, 4, 5 x-intercepts. So again, if we write, let me quickly write that. So if I write, well, how many was it? 1, 2, 3, 4 turning points, 4 less than or equal to n minus 1. Well, n has to be what? If you solve this inequality, add 1 to both sides, n has to be greater than or equal to 5, right? So this has to be at least fifth degree, right? And it has 5 real roots. Okay, so that's number 33. And what about a few more here? For the following, determine whether the graph of the function provides a graph of a polynomial function or not. And then if it does, determine the number of turning points and the least possible degree for the function. So here, can it be a polynomial function? Yes, because look, it has all real numbers for domain, no breaks, no sharp corners, and it doesn't approach any line or anything, and has 2 turning points here, right? All right, and what about, so it has 2 turning points, so the degree has to be at least 3, right? We talked about that. So at least to be 3. What about this one? Well, this one is not a polynomial because it's approaching what? A horizontal line, right? So this is not a polynomial. What about this one? Yes, and has 1 turning point. And what about this one? No, because this one has a vertical line here that is not crossing over here too. So there's a limitation on the domain on this one. So it's not a polynomial. And the last one I want to do is, let's do one with, it says for the following, graph the polynomial function using a calculator. Based on the graph, determine the intercepts and the end behavior. So we can do this with a calculator. And so what I'm going to do, I'm going to turn off my plot here. And I'm going to just put this function in there, x to the third power. and then times x minus 2. And then we're going to go to zoom 6 first. See if you can see a graph. Yes. What about zoom 4? Kind of a better graph, right? So it looks like the end behavior looks like on the right it goes to infinity, on the left also goes to infinity, right? And it says find the intercepts and the end behavior. Well, looks like if we trace over it, right? Looks like the y-intercept when x is 0 is y also is 0, right? So to find the y-intercept, all you have to do is go to table, right? And then make sure this independent is on ask, so you can put a number for it. If it's an order like this, right, you change it to ask and press enter, and then go to table here. That was table set. Now you go to table. And then delete if there's anything there, put 0, enter. That's the y-intercept. So the y-intercept is 0. And we go to graph. Now I want to find the x-intercept. Well, one of them, of course, is here. And you can zoom in. You see, if you trace, you go to zoom and go to 2 and press enter. You can zoom in, see? And then you can do the same, trace, and then zoom number 2 and press enter. See, it zooms in to see the behavior right close to the. Looks like the only place it's crossing the x-axis is at 0. So that's one intercept. So what I'm going to do, I'm going to zoom out now. We go back where we were. Let me zoom out one more time. Number 3 and enter. There. So we want to find the other one. So go to second, calculate, 0, number 2. So a calculator is going to start from somewhere. I showed you one of these already, but I'm going to go to in the other videos. I'm going to go to the left of that point, press enter, and go to the right of that point and press enter and enter again. So it's 2. So the intercept is 2. All right, we're going to talk more about this in the next sections. So I'm going to end this video here and then continue with chapter 5 in another video, okay? So take care, and so next video I'm going to talk about the rest of these. I talked about these two, and we're going to talk about the rest of this. So until the next video, take care of yourself and see you next time.